from UC Berkeley. He will tell us about isometric tensor network state on an infinite strip. So please start.
Okay, thanks for the introduction. My name is Sajant Anand, and I'm a graduate student at UC Berkeley. And today I'll be telling you about this tensor network algorithm for simulating infinite strip 2D systems using isometric tensor networks. First, to begin, I want to acknowledge my collaborators. So this work was done in collaboration with Yanta Wu, a postdoc at UC Berkeley, Shengchuan Lin, a graduate student at Munich, and my advisor, Mike Zalatel, at UC Berkeley. And the paper on this project is in preparation and should be out soon. This talk will have three parts. The first part is just to introduce isometric tensor networks first in their standard 1D form that we all are probably familiar with, and then go on to the finite 2D form, and then I'll introduce what needs to be done to get to an infinite strip geometry. In the second part of the talk, I'll then introduce the infinite Moses move, which is an algorithm that we came up with to manipulate this infinite strip geometry. And in the third part of the talk, I'll apply this infinite Moses move algorithm to perform imaginary time evolution on these infinite strips and find the ground state of transverse field Ising models in 2 dimensions. So to begin, I just want to motivate this with considering tensor networks in 2 dimensions. And the standard way that we have to study these systems is to use MPS methods. But these are inherently ill-suited for 2-dimensional systems. So if we consider this strip geometry where we have a 4 by infinity system, and we try to apply an MPS to it, we find that the necessary bond dimension chi grows exponentially with the width of our system. This is contrasted, however, with the fact that MPSs are very good at efficiently finding expectation values, as the cost of finding an expectation value scales as the bond dimension cubed. On the other hand, we can consider native 2-dimensional geometries for our tensor networks, such as the PEPs, where now we have efficient scaling with system size, but on the other hand, we have the drawback that contracting these PEPs tensor networks requires approximations, such as corner transfer matrix methods or boundary MPS methods. So what we'd like to do in the field of isometric tensor networks is to combine these two properties together. We'd like the efficient expectation value properties from 1D MPS methods, along with the efficient scaling with 2D system sizes from a PEPs. We combine these two together, and that's how we get to a 2D isometric tensor network state. So to begin, I first want to start off with briefly reviewing the 1D isometric tensor network. So as we know, any matrix product state can be put into an isometric form. So if we consider just the generic MPS on the left, we can perform a sweep of QR decomposition starting at the left or the right, and put this into a left, right, or mixed isometric form, where the arrows on the legs indicate that when we contract a tensor and its conjugate over the incoming legs, we get an identity on the outgoing legs. And this red dot here is the isometric center, or the orthogonality center, and this indicates that this is a representation of the wave function in the space of the physical leg and the 2 ancilla bond dimensions. The fact that we can do this exactly, moving from a standard MPS into an MPS in isometric form, has a lot of helpful properties, including the fact that local truncation is optimal. So if we focus on this orthogonality center in red, we can then do truncation in a principled fashion. As I've already mentioned, it's efficient to get expectation values of an MPS that is in isometric form because we just move the orthogonality center to the site we're interested in and then calculate the expectation value. And the third feature is that optimization is more stable and easier in this orthonormal basis. So moving to this isometric tensor network has additional benefits on being able to optimize for ground states. In 2 dimensions, however, exactly contracting a generic PEPs is exponentially hard. So what we'd like to do instead is consider a restriction of the PEPs ansatz that we term isoPEPs, or isometric PEPs. So in this case, what we've done is we've taken every tensor in the PEPs and replaced it with an isometry, shown in the bottom left. So now every tensor is an isometry. So again, if we contract over the incoming legs, we get an identity on the outgoing legs. From this diagram, we see that we have a special structure, this plus structure here, of blue and red tensors called the orthogonality hypersurface. And this orthogonality hypersurface is special in the fact that it has only incoming arrows from tensors that are not in the orthogonality hypersurface. So for example, on the top right, all arrows point in towards the blue plus, and the same in all 4 directions. This orthogonality hypersurface is analogous to a 1D MPS, such that when we're actually working just with the hypersurface itself, we can use 1D MPS methods. And just to graphically see, these black tensors have this constraint shown here. So contracting over the incoming legs gives identities, and similar with the blue tensors. This form of an isometric PEPS is especially nice when we're trying to calculate expectation values of local operators, shown here. So let's say we want to calculate an expectation value of operator O that's localized on this red site. Well, because of the isometric properties, this reduces down to simply this single contraction. So all we need to do is consider the orthogonality center, and because of the isometric conditions, all of the other tensors drop out. This extends to any operators that are within this orthogonality hypersurface, because then calculating the expectation value just reduces to a 1D MPS problem. But the question then arises, let's say we want to calculate a general expectation value that is not part of this hypersurface. What we need is an algorithm that allows us to move the orthogonality hypersurface freely through our isopeps. In one dimension, the orthogonality hypersurface is just the orthogonality center, and that can be moved exactly with a QR algorithm. In 2 dimensions, however, there is no exact algorithm, or at least we do not know of an exact algorithm that moves this orthogonality hypersurface around the isopeps. So instead, there was proposed an algorithm by Mike Zaltel and Frank Pullman called the Moses move, which has the purpose of taking a 2-sided MPS and splitting it into the pair of an isometric tensor product operator A and a new MPS phi. So this can be seen in the diagram on the right, where we take an initial 2-sided MPS psi, where we consider that we have the incoming physical leg, but we can also treat these horizontal legs, which are incoming, also as physical legs. And we split that into the product of an isometric operator A and a new MPS phi. And by this, we'll be able to move the orthogonality hypersurface 1 column to the right. And by the combination of this Moses move algorithm and then a generalization of the TEBD algorithm to 2 dimensions, we are able to perform imaginary time evolution on these finite squares and optimize it. Our goal in this presentation, in this project, was to move towards infinite geometries. So often in the case for 2D systems, when we use an MPS, we consider these infinite strips, where we're infinite in the vertical direction and finite on the horizontal direction. So that is the kind of geometry that we're interested in today. So we're going to consider this strip isopeps, where again, we're infinite in the y direction, and we have a finite number of sites in the x direction. Our unit cell is just going to be Lx by 1 number of tensors. So in this green box, that is our unit cell, and it's repeated indefinitely above and below. And our goal is to be able to manipulate and study systems on these 2D strip geometries. What we're going to need is first to develop an infinite version of this Moses move algorithm to move the orthogonality hypersurface between the columns. And then we're going to need to develop a TEBD squared, so a 2-dimensional version of TEBD, on this isopeps strip to perform imaginary time evolution and find ground states. So now I want to go into detail about how we actually do this infinite Moses move, which is shown pictorially in the top. So our goal is to take 2 columns. The left one is the orthogonality column. So this is just an infinite MPS, and then we have an isometric infinite column to the right, and then perform infinite Moses move, which moves this orthogonality column to the right. So for our splitting problem, let's just first set this up by considering in the right 2 columns at the top. The first is the orthogonality column, the second is just some general isometric column. And let's merge those 2 together to get some new column that we're going to work with. So this is our 2-sided MPS that we're interested in. On the top right, this is what we're really going to be working on, and we can just take the physical legs and group them into the horizontal legs, and this will give us our 2-sided MPS. So our goal is to take this 2-sided MPS, where each tensor is lowercase psi, and then split that into the product of 2 tensors, A, which is our isometric tensor, and phi, which is our new MPS tensor. So we want to split this column, capital Phi, into 2 new columns, A, which is our isometric operator, or isometric column, and our new MPS phi. Just to denote some of the bond dimensions that are going to be used here, the left leg and the right leg of this are not changed by the process, so chi L and chi R are the same in both sides. What we do have freedom over is choosing chi H, which is the bond dimension between A and our new MPS phi, as well as chi v and eta, which are the vertical bond dimensions of the isometry column and the resulting MPS column. By controlling these three parameters, so chi h, chi v, and eta, we'll be able to control the error of this splitting procedure. To quantify how well we're actually able to perform this splitting, we look for the A and the phi that maximizes the real part of the maximum eigenvalue of this transfer matrix T psi A phi. So that's shown graphically in the bottom right. So we look for the A and the phi that maximize the largest eigenvalue of this transfer matrix, keeping psi fixed. So this psi is not something that we're able to change. This is given by the input of the problem, and we're looking for an A and a psi, such that A is isometric and phi is a normalized wave function. So now what I would like to do is introduce two different algorithms that we use to actually perform this infinite Moses move splitting. The first is called, we call infinite Moses move Renyi, where Renyi indicates the fact that we're minimizing a Renyi entropy at some point of this procedure, which I will discuss in a second. So this first method, Moses move Renyi, all we really do is apply the finite algorithm, which was developed originally for these finite isopeps, and we apply this again and again until convergence. So this is a very brute force, naive way of doing this splitting procedure, where we just take our infinite column psi, and we just perform the finite algorithm over and over again. So let me now explain how this finite algorithm works. We're going to start with our infinite two-sided MPS psi, and we're going to randomly generate a tensor S that is not isometric, is just a tensor that is normalized. We then merge these two together. So we just contract along this vertical leg here, and then we group the horizontal legs so that we have a new object like this. We now want to perform an SVD in the diagonal direction to separate the left leg and the two other legs. And that gives us an object that looks like shown in the middle. What we have here is we have control over the bond dimensions of the two legs in the middle between the black and the red circle, because this is one way that allows us to control the accuracy of this splitting. At this point now, we want to split this red tensor into two different tensors along the direction of this dotted line. We note, however, that our goal is, after splitting this red tensor, to have the minimum bond dimension possible. So what we'd like to do is perform a disentangling procedure between the red and the black tensor along the vertical direction I'm tracing out with my mouse to minimize the entanglement that would remain after this splitting procedure. So our goal is to produce something now that looks like this. So our A is our new isometric tensor, phi is our new MPS tensor, and Sn+1 will be used in the next iteration of this procedure, replacing Sn. And we do this procedure over and over again until Sn and Sn+1 converge. And at that point, we take An and phi n and treat those as the results of our splitting procedure. One caveat is that you have to worry a little bit about gauge redundancies on these diagonal legs, but by imposing some gauge fixing procedures, we're able to get a result that performs quite nicely. So again, we take an Sn, we merge it in with our repeating tensor, we perform two different SVDs, and at this step, we perform a disentangling procedure, and the output is a new S, and then our desired tensors A and phi. And we repeat this over and over again. There's no guarantee, however, that this procedure will converge due to these gauge fixing procedures. So what we'd like to do is then follow this up with another algorithm called Moses move polar. So in this case, what we do is we iteratively use a polar decomposition to optimize the A tensor, the phi tensor, and the S tensor. So our goal is now to maximize this fidelity, shown in the bottom right, of this contraction of a tensor matrix. So again, we have our initial tensor psi, our S, which is the same in both places, and then the A and the phi that we're trying to optimize. And we iteratively go through this procedure and optimize A, phi, and S. For A and phi, which have isometric constraints on them, we find the environment of these tensors by contracting everything except that. We do a polar decomposition, and then the result of that becomes our new guess for A or phi. For optimizing S, we fix psi bar, which is always fixed because that's the input of our problem, And then we also have A and phi, the current estimates for A and phi from this polar decomposition procedure, and we find the leading eigenvector of the mixed transfer matrix. Where this is the fact that we're looking at, the leading eigenvector of the Hermitian transfer matrix of T and T dagger, where T again is a transfer matrix between psi, A, and phi. The reason that we're looking at the Hermitian part of the transfer matrix comes from the fact that S here appears on both sides of T. And I'd like to note that this is not variationally optimal, because ideally what we'd like is to find the leading eigenvector of the transfer matrix and not the Hermitian part of the transfer matrix. But I'll note a little bit later on that the fact that this I-Moses move polar algorithm is not variational optimal has not proved to be a major impediment to our work, as the results are still quite reasonable. And in fact, using a variational optimal method didn't improve considerably. So maybe just to recap this slide, because it's probably quite dense. Here, what I've wanted to do is introduce two different algorithms for performing this infinite Moses move splitting. The first is I-Moses move Renyi, in which we just apply the finite algorithm again and again, where we minimize a second Renyi entropy to get an efficient decomposition. And the second is an I-Moses move polar, in which we iteratively update our tensors A, phi, and S using a polar decomposition to improve upon the results. Let's now consider how well these algorithms actually do in practice. So what we're going to do is consider splitting an IMPS shown in the top right. So here's our two-sided IMPS with vertical bond dimension 128 and then bond dimensions of 4 on either side. We're going to split it into the two products, A and phi, shown on the right. I want to note here that we're going from a bond dimension 4 originally to a bond dimension 2 between A and phi. So we're doing some, we're not allowing for the maximum, which would be 4 by the isometric conditions. So instead, going from 4 to 2, we're guaranteed to get some projection error. And this is interesting to look at in just a moment. Again, for this A column, we have freedom to choose the vertical bond dimension, which we choose to be 2. And then for the phi column, again, we have freedom to choose the vertical bond dimension, which we're choosing to be 10. So in this case, the choice of bond dimension here for the phi column is akin to a 1D MPS truncation problem, because phi itself is just a 1D infinite MPS. So again, making this 10 larger will improve the results, directly analogous to increasing the bond dimension of an MPS. So to analyze the performance of our algorithm, we'd like to talk a little bit about the error from doing this procedure, the splitting procedure. So what we'd like to do is consider the error between our original input, psi, and our output, A, phi, or lambda. And what we do is the error per site, we're going to decompose into two different error terms, a projection error and a truncation error, where those two are given below. Rather than get into the mathematical weeds of how these two come about, I'd just like to note that the projection error is largely controlled by the fact that we're going from an input bond dimension 4 here to an input bond or output bond dimension 2. So this is where we're projecting the horizontal bond down. And the truncation error is the fact that this MPS will be truncated following this disentangling procedure. So what we'd now like to look at is the performance of our different algorithms and see how well they do, as well as how long they've taken time, and figure out which is the one we should use throughout our experiments. So in this table, we show results for the Renyi, the I-Moses move Renyi method, where we just apply the finite method over and over again, the iterative polar method, RP, in which you first start with the Renyi and then improve upon the results by doing this iterative polar method, and finally RPC, in which you do the Renyi first, then do polar, and then finally do a conjugate gradient procedure that improves further upon these results. We note that the conjugate gradient procedure, which I didn't go into any details here, but this conjugate gradient procedure is variationally optimal, so this would be the golden standard of splitting algorithms to do, but as we see from this table, it doesn't actually end up being necessary the majority of the time. So looking at the projection error and the truncation error, we can see that in most cases, this third algorithm, RP, in which we first do the Renyi and then we do the polar, is sufficient in that it is both fast and gives results comparable to the RPC, or the method with conjugate gradient. So in all of the experiments that we show next, we're going to be sticking with this RP method of doing this I-Moses move splitting procedure. Another question to ask is, how does this isometry A in the splitting function as a disentangler? So let's consider the following splitting problem on the top right. Again, we have our two-sided MPS. We want to split it into the product of an isometry column A and the new MPS phi. What we're going to do is we're going to fix all the bond dimensions except for the vertical bond dimension of A. So we're fixing this horizontal bond between A and phi to be 4. So we're doing projection from 8 to 4. And we're going to fix the vertical bond dimension of our new MPS to 8. We want to ask, how do the errors scale as a function of this A? Remember, the purpose of this A is to perform a disentangling effect on psi, or on phi, this new MPS, such that it is easier to split and easier to truncate. As a benchmark, let's just take our original MPS psi and truncate it down to bond dimension 8, at which point we get an error of 1 times 10 to the minus 1. So this is to be expected that we're having a very large truncation of the bond dimension from 128 to 8 directly. We want to see how this changes as a function of chi v. So what we've done here is just calculate the errors of this splitting procedure as a function of chi v, so as a function of the vertical bond dimension of A. And what we notice is that as chi increases, both the projection and the truncation errors decrease by several orders of magnitude, indicating that this isometry column A is doing a very good job of disentangling this wave function and allowing for an efficient splitting of the two-sided MPS. So again, in blue, we have the projection error, which is the error going from bond dimension 8 to bond dimension 4, and we see a great reduction as chi increases. And similarly, in orange, we have the truncation error, which is the error of truncating this phi to bond dimension 8. We note that if we just truncate this MPS directly, we have an order of 10 to the minus 1, but already with a bond dimension 1, vertical bond dimension 1 column A, we're already able to reduce that error by several orders of magnitude. So this procedure is providing a large benefit to this splitting. Finally, we should ask the question of how does this state change with repeated applications of this infinite Moses move? So as I mentioned earlier, this Moses move is not an exact algorithm. So moving this orthogonality column throughout your ISO-TNS is not an exact procedure. So we would expect that repeatedly performing this infinite Moses move would cause some error to accumulate in our system. So what we're going to do to test this is start off with a desired ISO-TNS, psi 0, with bond dimension chi 0, and we're going to repeatedly sweep left and right, back and forth over this ISO-TNS. So again, we have an infinite strip that we start with, that bond dimension chi 0. We then perform this infinite Moses move to move the orthogonality column to the right, and then we go back to the left, and then back to the right, and over again. And this gives us n new different infinite strip ISO-TNSs. We also have the freedom to choose the bond dimension of our new strip ISO-TNS, and that allows us to see the following results. So what we've done is calculate the 1 minus the largest eigenvalue of the mixed transfer matrix between our original ISO-TNS and our current ISO-TNS after n sweeps of Moses move as a function of the sweep number. And additionally, we've shown how this scales as a function of the bond dimension chi. So we're changing the bond dimension of the ISO-TNS. And what we see is very encouraging in the fact that the error seems to stagnate or not grow linearly as a function of sweep. So if we just consider this 1 minus the largest eigenvalue, the error seems to tail off as we do more and more sweeps, indicating that although I-Moses move is an approximate algorithm, we're not getting progressively further and further from the desired starting point, which is our initial ISO-TNS. Okay. So with having introduced this infinite Moses move algorithm for moving the orthogonality column throughout this ISO-TNS, I now want to talk about how we can perform a ground state search by imaginary time evolution. So to begin, I just want to review the finite algorithm called finite TEBD squared, where we call it TEBD squared because in essence, we're going to be doing TEBD inside of a nested loop, once over the columns and then once over the rows. So as is the case in imaginary time evolution, we're going to be applying operators e to the negative tau h to our initial starting point psi 0, with the goal as tau goes to infinity, our ground state will be proportional to the result, but unnormalized. So let's just consider how this works. We're going to consider Hamiltonians that can be written as the sum of column terms and row terms. So capital HC plus capital HR, where each term in HC or HR is a two-column gate. So we're saying that our Hamiltonian is the sum of two-column gates acting on rows and then two-column gates acting on columns. So this is, for example, the transverse field Ising model is the one that we considered here. So to begin, we want to consider our iso-TNS ansatz and the finite case shown here with the orthogonality center in the top left. So our plus shape orthogonality column, or orthogonality hypersurface, is the leftmost column and the topmost row. The first thing that we do is, when considering just this column, is perform one-dimensional TBD just on the column. So here we're taking the first set of column operators and applying TBD going downwards. What this does is move the orthogonality center from the top all the way to the bottom, as in standard 1D TEBD, so that after this procedure, we've now moved the orthogonality center to the bottom of that column. And we've applied the first column's worth of imaginary time evolution. We now need to move on to the second column, and we can do this by using the finite Moses move algorithm to split this orthogonality column into two new columns. The first one, which contains the physical legs, is our isometric column A, and our new orthogonality column, MPS, called phi. We can then take this orthogonality column phi, which does not have any physical legs, and merge it with the next column to the right. And now we have effectively moved our orthogonality column one column to the right, while also applying imaginary time evolution gates to the first column. We can then repeat this procedure over and over again, so doing TEBD down the column, and then Moses move to move it up and to the right, and eventually what we'll get to is an iso-TNS where we've moved our orthogonality column all the way to the right, while applying time evolution gates to each of the columns. We can then do the same procedure using time evolution gates on the rows to move the orthogonality center to the bottom right, and then again back to the bottom left, again acting on the columns, and then back to the top left, acting on the rows again. So we can have this cyclic procedure going from top left to top right to bottom right, to bottom left to top left, over and over again. And in this way, we'll be adding more and more time evolution on top of our state and moving towards the ground state. Just to note on the complexity, this procedure has a computational cost of chi to the 7th, where the TEBD itself with the reduced update approach has cost chi to the 6th, but then the Moses move algorithm has cost chi to the 7th. So overall, it's chi to the 7th. And we can compare this to full update for PEPS, which is perhaps the one we wish to compare to, which has a cost of chi to the 10th. I just want to note that to get this cost of chi to the 7th, we consider that every bond dimension in the iso-TNS is going to be chi. And that's how we get a dimension of chi to the 7th. So just to consider how well this works for the finite case, we can look at the difference of energy between an IMPS found by DMRG, because these are finite systems. We can do DMRG on a strip and get the reference energy to compare to, and then calculate how this performs as a function of both bond dimension. So here blue is 2, orange is 4, and green is 6, and as a function of the Trotter time step. So as we'd expect, increasing the bond dimension of the iso-TNS improves our results. What we want to do now is extend this finite algorithm for working on a finite square or a finite rectangle to our infinite strips. We're going to do something very similar. There's a couple changes. First being that rather than working with a Hamiltonian as a sum of row operators and column operators, we're going to instead consider Hamiltonians that can be written as a sum of two column operators. So we're going to group two column operators together and then write our Hamiltonian as a sum of that. So first a column operator acting on columns 1 and 2, and then 2 and 3, and 3 and 4, and then so on. The goal of this is that each of the column operators will be infinite because that's our infinite dimension, but each term in the column operator will actually act on a plaquette of sites, so this square. This actually is quite nice for us because this allows us to work with models that have diagonal couplings as well as vertical and horizontal couplings. So again, to walk through this, we're going to start off with an iso-TNS with the orthogonality column all the way on the left side, denoted by the blue. Considering just this, we're going to merge two columns together, so now each site has two physical legs. We're then going to apply our time evolution operators to this two column, so this merged column, moving the orthogonality center from the top to the bottom. So again, we're essentially just converting the form of the IMPS from right canonical form to left canonical form. So once we've done that, we've applied all the operators and we're ready to then apply Moses move to our procedure. So we want to split this two column into now an isometry column and our new orthogonality center. So we apply the iMoses move algorithm, and that brings us to this step. So essentially what we've done is by a combination of one-dimensional TBD, or ITBD, and then iMoses move, we're able to apply imaginary time evolution operators and then split the two-column conglomerate up into two separate columns. We can then repeat this procedure again and again until we get to the end of our iso-TNS. But unlike in the case of the finite algorithm, we don't need to separately consider the row terms because those were considered in our plaquette. So instead what we do is just sweep back and forth, left to right to left to right. So each time we sweep from left to right, we're doing one iteration of the time evolution. And then depending on how large your desired beta is, that determines how many sweeps of this procedure you make from left to right. One additional caveat is that we're going to introduce auxiliary legs on the boundaries. So what we've done is added these additional incoming legs on the boundaries where we're going to give bond dimension dB or chi. So this is going to be consistent with the rest of the iso-TNS. And these additional legs function as a purification in the sense that we can now represent, similar to in 1D, how adding auxiliary spins to your sites allows you to represent mixed states or finite temperature states. These auxiliary legs can be thought of as doing the same thing, but the reason that we introduce them is that they relax the isometric conditions so that now you have a larger incoming bond dimension, and this makes the iMoses move procedure of splitting the legs easier. So this is just a technical detail, but we expect that as we cool to the ground state, the presence of these additional legs isn't really going to matter that much because the ground state is a pure state and should be able to be represented with dB equals 1. I just want to note the computational complexity of this algorithm. So again, it's O chi7th from the Moses move, but then the cost scales linearly with the width of our strip, which is a very nice and key property of this two-dimensional algorithm, and that compared to the 1D DMRG or 1D algorithms on a strip, which the cost scales exponentially with the width of the strip. Now we have that the cost scales linearly with the width of the strip because increasing the strip's width just means that we have to do more iterations of this TBD and Moses move procedure. It's just sweeping back left and right. So let's consider how well this procedure actually does. We're going to consider the 2D transverse field Ising model with G equals 3.5. So this is within the paramagnetic phase. And I want to introduce one additional parameter that we have to play with, which we term F. So when doing this splitting procedure from our two-sided MPS into our new product, we're going to allow the bond dimension of phi to be some F times chi, where we are going to be allowed to tune F, with the idea that the larger F gets, we would hope that the more accurate this procedure gets. So we've considered two cases here. The first of an Lx equals 8 by infinity strip, and the second by a wider Lx equals 20 by infinity strip. We note that in both these cases, this is getting wide enough that it's difficult to solve using IDMRG for an IMPS. So we're really trying to get into the regime where we expect these 2D algorithms to show their benefits. So what we have here again is the difference in energy per site compared to some reference DMRG values as a function of the Trotter time step for both chi equals 6 and chi equals 8 iso-TNSs with different f values. So we're increasing the value of f, this parameter that controls the bond dimension of phi. And what we notice is that, again, chi equals 8 does do better than chi equals 6, as we'd expect. So increasing the bond dimension improves the performance as a result, and that we are able to see performance that's consistent with the finite algorithms shown on a 6x6 square. When we consider the Lx equals 20 by infinity case, we actually find that when we go to Lx equals 8, we can get lower energies than possible with IDMRG, which makes intuitive sense in that we're finally getting to the regime where these 1D algorithms aren't capable, even with large bond dimension, of accurately capturing the state. So by doing this TBD squared algorithm on this strip isopeps, we're able to get lower energies than IDMRG for this Lx equals 20 by 8 system. A question that ought to be asked at this point is how much better can we do, and how powerful is our strip isopeps ansatz? So let's get an energy upper bound for our geometries. So let's consider an IMPS that we found from IDMRG, shown in the bottom left, and first collapse that to a single column. So all we've done is taken all the tensors in a unit cell and contracted them together. So now we have a single IMPS with 4 physical legs. We can then repeatedly apply Moses move to this strip and pull off columns like so, and eventually get to an isopeps. So we started with an IMPS, and we've turned that into an isopeps just by repeatedly applying Moses move. And what we want to do is now consider how well this performs. So what we're looking at is Lx equals 4 and Lx equals 6 strips with bond dimension 2, 4, 6, and 8, and the results of this energy from peeling and then doing this TEBD procedure. And we see in all but one of the cases, this peeling procedure of taking an IMPS to an isopeps actually gets better energy for these smaller strips. This to us indicates that this TEBD algorithm is not saturating the full power of this isopeps procedure, but instead we need different optimization algorithms. So to end my talk, I just want to highlight 2 different ways that have been proposed. The first is a method called DMRG squared in a recent work by Xingxuan, one of the collaborators, in which, similar to how TBD squared does TBD on the rows and the columns, you can do DMRG both on the rows and the columns of this isopeps. The benefit of working with an isopeps compared to a regular unconstrained peps is that we're able to convert the generalized eigenvalue problem for optimizing a site into the regular eigenvalue problem, because this norm matrix N is just the identity because we're working in an orthonormal basis. What they found was that DMRG does perform better than TBD squared for a fixed bond dimension, shown here. So again, blue is 2, and then orange 4, green 6. So we're able to improve the results by doing this DMRG procedure compared to TBD. However, the cost of DMRG squared is larger than TBD, so that's something to be considered. An alternative approach that's quite interesting is to instead try to optimize using gradient-based procedures. And there's 2 main strategies for doing this. The first is to analytically calculate the gradient by a sum of tensor network or tensor diagrams, where in an infinite geometry you'd have an infinite sum of these tensor diagrams. And then on the right side, we can instead consider automatic differentiation methods that have become popular quite recently. And this is a project that we're currently doing in collaboration with Lorenz van der Straten at Ghent and Frank Polman at TUM, and we're quite excited about using these gradient-based methods to optimize our isopeps. So finally, in conclusion, I just want to note that what we've done here is introduce an iMoses move algorithm to split this 2-sided peps shown in the top left, and that this procedure actually has a strong disentangling effect, and that this A greatly reduces the errors of just truncating phi originally. So we expect this iMoses move algorithm, or the finite algorithm, to have applications outside of just 2D isometric tensor networks. We've also noted that by this TBD squared algorithm, we have an optimization algorithm that scales linearly with the strip width, which is very exciting as we get to larger and larger strips. But we note that there is room for improvement in optimization, and this is the subject of future work. With that, I want to thanks and take any questions I have in the small amount of time left.
Okay, thank you very much. So nice talk. Now this talk is open for the questions and comment. So if you have any question or comment, please raise your hand. So I have a question about the energy calculation. So I naively feel that because this modest move has some error, the energy can be lower than the exact energy. Is that correct?
Well, yes. So that is one thing that we certainly looked into, in that the way that we're So the way that we're actually getting the energy is, in the procedure of this Moses move. When applying the TBD, you can also calculate the expectation value of these two-site operators. But then there's also two additional different ways of calculating the energy. We can do regular PEPS boundary MPO methods, and then we can also just contract this strip IsoPEPS into an MPS and use regular MPS methods to calculate the energy. And what we've done is we've shown that each of these three methods, so calculating the energy by during this ISO or TBD squared procedure, the boundary MPS, and then the regular MPS methods all give very consistent energies. So we feel confident about this.
Okay, so your negative delta E means that truly you obtain a good result.
Correct, yes.
Yeah, thank you. So next, Ian, please.
Oh, hey, yeah, nice talk. Just the boundary condition. So often when you do IDMIG for these cylinders, you have periodic boundary conditions around to make it a cylinder kind of geometry. Can you do something here like that?
So at the moment, the way that we did this is just by operating with two-column operators. So just working with the sum of these plaquette terms. So in that respect, it's hard to do this periodic boundary conditions where you would need a longer range interaction. I will note that in some of the ongoing work with this gradient descent work that we're currently doing now, this is no longer an issue, and that we're working with MPOs to do the optimization. So I think for those algorithms, which aren't quite finished yet but are progressing quite nicely, then we'll be able to actually directly compare to cylinder DMRG results, and then hopefully move to larger and larger systems where cylinder DMRG is no longer applicable.
Okay, thanks.
Any other questions? Harada-san, please.
Thank you for nice talk. I want to ask about the role of this entangular in your algorithm. So you defined two types of error. One is projection error and one is
yes, and then the truncation error.
Truncation error. How to define each error?
Okay, yes. So our goal is to split this original MPS psi into two things, an isometric A and a new MPS phi. And then we note that this isometric A has a property that A dagger A is the identity because it's an isometry. So what we really want to do is the original error, or the total error, is going to be 1 minus the maximum eigenvalue of the regular transfer matrix squared. And we're going to decompose that into the truncation and the projection errors. So the projection error is going to be the error of this state A dagger psi from this transfer matrix, where A dagger psi is not normalized. So this is the projection error, and this results from the fact that we're going from a bond dimension 4 to a bond dimension 2. So we're having projection in the horizontal bond. On the other hand, we can get a truncation error by considering the mixed transfer matrix between our new MPS phi and then an MPS of A dagger psi, where we normalize this, where the result of A dagger psi now, this bond dimension will be, this left bond dimension will be the same in both cases. So we can then form a transfer matrix and again look at the maximum eigenvalue of this. And this captures how much error is coming from the truncation of this phi from its optimal value.
You show about the performance of this entangular in another slide. So this one. So this figure shows that if we increase the chi v, so the power of this entangular increase.
Correct. So the idea is that this tensor A is becoming larger and larger, and that the horizontal dimensions are fixed to be 8 and 4. So we're seeing that even in the case where we're fixing 8 and 4, so we we're guaranteed to be doing some projection from a bond dimension 8 to outgoing bond dimension 4. And we've also fixed the truncation of the new MPS phi to be dimension 8. And we're showing that as we increase the power of this disentangler, both of these errors are decreasing by several orders of magnitude. So this procedure of doing this imoses move, going from our original psi with larger bond dimensions to our new products of A and phi with smaller bond dimensions, we're able to decrease the error by making this isometry more and more complicated. And in fact, this is the behavior that we think, we find very encouraging and think might be useful in other applications, even in cases where you just have a two-sided MPS. Because we're able to perform this splitting procedure more efficiently than just naively doing it.
Thank you.
Do you have any questions or comment? If not, let's thank the speaker.